I want to pick up where we stopped last time with a couple of examples, just to sort of give some context to why we talked about these things. And these will be pretty quick. No big surprises, I think. Verify that y equals 1 over c minus x is the solution to the differential equation y prime equals y squared. Okay, well, so quick refresher, what do we do when we want to verify something? Plug it in. Yeah, plug it in. Okay, so let's just check. So y is 1 over c minus x. If you like, you can even write that as c minus x to the minus 1 power. What is y prime? Now, if we do it in this format here, what rule would we need? Chain rule. It's a good rule. Okay, so according to the chain rule, what do?
Derivative of the inside.
Well, there'll be a derivative of the inside at some point, but where do you start usually?
Outside.
Take the derivative of the outside, which is the minus 1 power. So you bring the power down. C minus x to what new power? Negative 2. You subtract 1 from the power. Minus 1 subtract 1 is negative 2. And then people mention the derivative of the inside, which is minus 1. Which, of course, 2 minuses make a plus. Just as we know from young children, 2 wrongs make a right. And so that becomes c minus x squared, because the minus 2 just means to move it downstairs. But wait a second. That looks a lot like 1 over c minus x. What's the difference? You squared it. So that's y squared. Oh, well, that's what we wanted. Woohoo! Another thing has been verified. We're getting really good at this verification stuff. All right, verification. We're going to knock that out of the park if they ever ask us to verify stuff. Now it says find the particular solution, which satisfies y of 3 equals 2. Now that, when you say find the particular solution, it's like solve for c. That's what that really means. Okay, so how do you solve for c? Yeah, we use our initial information, these initial conditions. So this is really saying when you plug in x equals 3, you're getting out y equals 2. So we come to our function. We say, okay, so 2 should equal 1 over c minus 3. Well, what are some things we can do? So you can do a couple things. You can do, people mentioned multiplying, there's something called cross multiplying. The idea of cross multiplying is you can imagine that there's a little over 1 here. You multiply here and you multiply there, which is great. And if you did that, you would get 2 times c minus 3 equals 1. Or 2 times c minus 6 equals 1, I think. Oh, that seems right. So then what?
Add 6 each time.
Add 6. Our, algebra. This is great. This is our bread and butter. We love algebra. And so that tells us that c is 7 halves. Okay, good. Now, by the way, there are other things that you could have done. So this is a fun thing. The further you go in math, the more options you have. So another thing you could have done is said, hey, let's not cross multiply. Let's just flip both sides. So if you did that, you'd get 1 over 2 is c minus 3. And now what do you do to solve for c? Add 3. Well, 3 is the same as 6 over 2. 6 over 2 plus 1 over 2 is 7 over 2. Yeah, lots of choices, lots of choices. All right. So, well, we wanted our c. We want our particular thing. So it's 1 over, and we can have 7 halves minus x. And there we go. Now, if you don't like fractions within fractions, you could multiply top and bottom by 2. You could say, oh, this is like 2 over 7 minus 2x. Okay, great. They're both the same. Doesn't really matter. Okay, so that's good. Now the question. What can we conclude about y of 5? So we had our differential equation. We've now solved it. We have our function. So what do we do if you want to know what y of 5 is? Yeah, we should plug it in, right? Ah, I see people haven't been in my classes before. Good. All right, let's plug it in. Let's do it. Do it. Okay, so plug in 5. All right, well, if we do that, we'll get 2 over 7 minus 2 times 5. Okay, 2 times 5 is 10. 7 minus 10, that's minus 3. So minus 2/3 is what it would come out to be. And you're like, okay, well, so let me be more careful. Y of 5. All right, so is this the answer? Question mark. It feels like it, doesn't it? It's like we solved the differential equation, Steve. We have a function, Steve. Plug it in. How could it not be the answer? Are you trying to trick us, Steve? And we know you are because we've seen you before. You're a trickster. You're a trickster. Is that the right answer? And I know you want to say yes. Oh, people are torn. They're torn. They're like, I don't know. I don't want to fall for Steve's trap this early in the semester. Okay. It turns out this is not the answer. And I'll tell you what is the answer. The answer is we can conclude nothing. That is the correct answer about y of 5. We have no clue what y of 5 is. Now you might say, wait, how could that possibly be? We have a function. It solves the differential equation. It solves the initial value. We can plug 5 into that function. Life is good. What's the problem? Well, let's talk about this function. Y equals 1 over 7 halves minus x. Can anyone tell me anything about this function? Well, okay. Someone said it's a solution. Someone mentioned the word asymptote. So it does have an asymptote. Where does the asymptote happen? 7 halves. Okay, so if we were to sketch this function, we would say here at 7 halves, if we can find where 7 halves is, and we'll say this is 7 halves here. There's an asymptote. So below 7 halves, it looks like this, and above 7 halves, it looks like that. So there's our function. This is what our function looks like. Okay, now, where was our initial condition? In other words, in relationship to 7 halves, where does 3 lie? To the left or to the right? To the left, to the left. When we picked 3, we chose it to the left. There was our initial condition. All right. Where are we trying to ask a question about? 5, which is to the right. And nobody sang the song. I'm kind of sad. All right. So here's the thing. Is when we talk about a solution, really we're saying, how is our function changing and where do we start? And the problem is you cannot push past an asymptote because your solution should move along the curve. And as we move, we know we start, we move, we start, we move. The problem is I can't get past an asymptote. And so anything that happens to the left of this asymptote has no influence on what happens to the right. So we can't actually know what this function does after it blows up because there's no way to push past that point. So asymptotes can be bad. And there's nothing about this that says, hey, you're going to hit an asymptote pretty soon. Sometimes it just happens. So that's just one thing to be aware of. All right. Well, now we'll do something that's clearly not so tricky. A second example. All right. So, given that xy prime equals 3y, show that y equals some constant x cubed is a general solution. Okay. All right. So let's just do that. Here we go. So do what we did before. X, let's just remind ourselves y looks like some constant x cubed. So what is xy prime? Well, that's x. What's the derivative of some constant times x cubed? 3, the constant, x squared. So there's our y prime. Well, we can do some things. We can move the 3. We can put the x with the x. And so that would be 3 times a constant x cubed. But what is that?
3y.
So what is this part?
Y.
Well, I'm asking you the question so we can solve the problem. That's why. Oh, you meant y the variable. I'm sorry. Okay. 3y. Okay. And so now what do we see? We see that we verified it. We're happy. Woohoo! Check mark. It's been verified. xy prime equals 3y. Exactly what we needed. Okay, so we've done that first sentence. We've shown it. If we are also given, oh, there's even more now. Okay, y of 2 equals 4. All right, so y of 2 equals 4. So really we could say, okay, so 4, which is y of 2, should be some constant c times 2 cubed. Okay, 2 cubed is 8. 8 is enough, good. So what should c be? A half. All right, so it says find a particular solution. So now we have that our particular solution is y equals 1/2 x cubed. Beautiful. We're just like powering through here. Now, the last question. What can we conclude about y of -3? So we have our solution here. It's a very nice solution. Are there any asymptotes? No. Okay, good. Nothing could trick us up. No way can Steve get us twice in a row. No way could he do it twice in a row. So, if I want to know about y of -3, what should we do?
Plug it in.
Yeah, we should plug it in, right? So it's 1/2 -3 cubed. Anybody know what -3 cubed is off the top of their head? Oh, good. Oh, you like cubes. Okay, good to know. All right, so now the question. Is this the answer? Question mark, question mark? All right, are you ready to know? The question was, what can we conclude about y of -3? The answer is nothing. Now, at this point, you're thinking, this differential equation stuff is not very useful. We can't make anything. We learn nothing from solving differential equations. But wait, hold on. What's wrong? There's no problem with the function. Let's look a little bit at our differential equation. Okay, so xy prime equals 3y. Now, you may remember that we talked about in passing, when we solve these, you think about y prime equals everything else, f of everything else. So you should solve for y prime. So here we haven't solved for y prime. All right, so what is y prime? 3y over x. Now, we know that we're fine as long as f of xy is a nice function. We'll come back to this in a second here. Let's talk about the function 1/2 x cubed. Anyone have a rough idea what it looks like? Willing to do some modern interpretive dance? It looks like this kind of thing. Anyone? No brave souls? Okay, all right. All right. I'll tell you what it looks like. It looks like the cube function. So this is what y equals 1/2 x cubed looks like. Now, looking at this function y prime equals 3y over x, are there any places where this is worrisome? Or f of xy not nice? Yeah, the problem is right there. When x equals 0, you have a division by 0 problem. Now you might say, well, yeah, but our solution pushes through there, right? Well, a solution passes through there. Now here's the thing. The function y equals a half x cubed, this function is in fact completely correct up to the point where we hit 0. The thing is, we cannot guarantee that anything that happens past that point, because the differential equation is breaking down. And in particular, it turns out that the general solution to this differential equation is not some constant x cubed. It really has the following form. It's some constant x cubed for x above 0, and some constant x cubed for x below 0. And a and b can be chosen arbitrarily. So in other words, even though it has one behavior on one side, it could have completely different behavior on the other side of 0. So it might be coming down steeper, it might be coming down shallower, it might be coming up here. All of these are valid solutions. And all of them pass through our initial point of y of 2 equals 4. All right. Now, after I've shaken you a little bit, the punchline. The important takeaway. So, solutions of differential equations are valid. And I want to say the differential equations we're going to act with are going to be fine. The only things we have to worry about is either the function breaks down, look for asymptotes, or the differential equations breaks down. That's where y prime equals f of xy, and the function f is not nice. As long as those things aren't happening, which is going to be essentially all the time, we're fine. We're fine. But mathematicians, we have to worry about these things. So now you get to worry a little bit too. But, all right. So that is the discussion from last time. Now, any questions before we move on to today? I think there's a question.
Are holes in a function fine?
Well, holes in what?
In your general function.
Well, usually when you have a function that's a solution, you won't have a hole. The hole won't be there. Now, if you have a hole in your differential equation, then that's a breakdown. And yeah, that's something's going to break down. Now, you might say, well, what if our f of xy is not continuous? Can I still have a nice solution? Well, yes, because it can be not continuous in x and be fine. And we'll do some examples of that at some point during the semester. All right. So on to today's topic. So we're going to talk about very simple differential equations. Essentially, it's just sort of a deja vu, because we took calculus, it's a prerequisite, and it says, what if I have a differential equation of the form y prime equals f of x? Well, there's a whole class for that. Actually, there's like a class and a half. Calc 1, you get to start that. In Calc 2, you really get to turn up the heat a little bit and solve even more fun parts. You say, well, the way you do it is you take the integral of both sides, or if you like, the antiderivative of both sides. So our solution is you find the antiderivative, and don't forget a plus c. And you can even do particular solutions. You can make it very explicit. And so if I want y prime to equal f of x, and y of a equals b, then you can say, here's a very explicit solution. You b plus the integral a to x f of t dt. Now, we almost never write our answers this way. We just say, find the general solution, solve for c. Well, let's actually verify. All right, what happens if you plug in a equals b? Plug in x equals a. If you plug x equal a into here, you have b plus the integral from a to a of f of t dt. So, does anybody remember what is the integral from a to a of f of t dt? 0. Yeah, because it's like trying to find area, but there's no width. And so this part equals 0. So you get that, aha, y of a equals b. Okay, what about y prime of x? Well, what's the derivative of b? 0, because b is a constant. So y prime of x is the derivative from the integral from a to x of f of t dt. Well, what's that what's that derivative? It is? Some people are saying f of t. Some people are saying f of x. A lot of people are saying, I don't know. Or I'm just shy. I don't like to give the answers away. It is f of x. In essence, the t here is involved in the integral. It goes away with the integral. The thing that's changing is the x. So it should be something that depends on x. By the way, this fact has a nice name. Do you remember it? Fundamental theorem. You can't spell fundamental without fun. You know, so it's a great part of calculus. So, all right. So I know you're like, these are easy. Yeah. Oh, maybe. Some can be challenging, but we should try these. All right. Find the general solution. dy dx equals 3x square root of x squared plus 9. Okay. So what do we do? Take an integral. Yeah, exactly. For y prime equals f of x, the idea is you're integrating both sides. That's the philosophy. So we integrate. Integral of dy dx is y. Integral of 3x squared of x squared plus 9 is 3x squared of x squared plus 9. Why not? We'll start there. Okay. Well, how can we approach this problem? Well, someone said trig sub. I was going to say, you know, if you don't like yourself, you could try trig substitution. But I'm in the philosophy that we love ourselves. You know, we deserve a break. So we should avoid trig substitution if at all possible. And I will say that for the vast majority of the semester, I don't think we're going to do very much trig substitution, if any at all. Maybe once or twice for funs. But trig sub is a beautiful idea. Don't get me wrong. I'm a big fan of trig. Square root of x squared plus 9, that's not a very calculus way to write that. What's a better calculus-friendly way to write square root of x squared plus 9? X squared plus 9 to the 1/2. All right. Now, what's in the pantheon of ideas for integration? What's sort of like your go-to thing to check for? Use substitution. If you can't integrate it right away, you say, let me see if there's a nice substitution to make. That's like one of the first things you should always check. Is there a nice substitution? The x squared plus 9 is a great. Remember, substitution, I like to think of it as substitution is the inside job. So you're looking for something on the inside. So x squared plus 9, that's on the inside. All right, u equals x squared plus 9. What would du become? 2x, throw in a dx. You're like, oh, what a shame. We had a 3. So close. No, come on. We can make that work. We'll just put a 2 here and a 1/2 there, and life is good. Right? Because we can throw constants around. Constants are easy to do. Okay, there's other ways to do this, but all right, so if we make this substitution, well, we have the 1/2. The 3 we can put out with the 1/2. So we have 3/2. The 2x joins with the dx to give du. And what's the rest of it? U to the 1/2, or square root of u, but u to the 1/2 is more calculus friendly. The reason I say it's more calculus friendly is it fits the rules. What's the integral of u to the 1/2? U to what power now? So what? 3 over 2. And the way you get that, you add 1. Anything else? Yeah, I got to multiply by the reciprocal, 2/3. And curiously, almost as if they had planned for it to happen. It's just right. Just right. Wow. What nice people. Is there anything our answer is missing? Plus C, yeah. Remember, that constant is important. Okay, is that our answer, and why not? Got to get it back, right? U substitution puts it in terms of U, but we started in X, so we need to end in X. So our final answer will be X squared plus 9 to the 1/2 plus C. And remember, this is Y equals that. 3/2. Yes. Good. Thank you for catching that. And that's it. That's not so bad. So, all right, any questions on that one? Yes?
1/2 that's outside. Let's go like before using substitution. Where did you get that from?
Well, so I wanted to, there's a couple ways you can think about it. So I said, hey, it would be really cool if there were a 2 here. So the question is, why is there a 1/2? Well, I put a 2. But if I put a 2, I can't just introduce something unless I introduce 1. I can multiply anything by 1, and I can add anything with 0. And I'm good to go. So 2 times a 1/2 is 1. So I said, aha, if I put a 2 here, and I put a 1/2 simultaneously, it's like multiplying by 1, life is good. So that's why I had to have the 1/2 to compensate for the 2. It didn't have to be on the outside. It could have stayed on the inside. There's another way you can do this. Sometimes, you know, it's like 50-50. The other thing I would do is say, here I have x dx, I put a 1/2 du. And then I say, this x dx would introduce 1/2 du, and then the 1/2 would show up. So that's another way to do it. And I'm not saying one way is better. I'm just saying do it the way that you won't make a mistake. Because it turns out mistakes lead to wrong answers. And we don't want those. We want the right answers. Given that x double prime of t equals 15 square root of t plus 3, that x prime of 1 equals 90, and x of 1 equals 140, find x of t. All right, so we have the second derivative. We want just a function. So how many integrals do we get to do? 2. Oh, this is so cool. We get to do 2 integrals. Oh, we're so lucky. You know, those people who only get to do 1 integral, they're missing out. All right, we'll write as t plus 3 to the 1/2. And now if we do the first antiderivative. Okay, the 15 is a constant. And here, t plus 3, there's nothing fancy here. We don't need to do anything too. If you really wanted to, you could do some substitution. But this is one that we hope you get to the point you don't need to substitute. So if we didn't need to substitute, we could do it in our head. What would the antiderivative look like? Well, you'd have t plus 3 to what power? 3/2. And then we'd multiply by 2/3. And then tack on a plus c. Now, why do we get away with that here? Well, because it's the variable plus a constant. There's no like t squared or t cubed or nothing. It's just t. So this works just as if it were a normal t instead of a t plus 3. Or if you like, that's the same as 10, t plus 3 to the 3/2. Now, does the c need to be involved with the 10? The answer is no, just leave it by itself. One of the things about constants we're going to say is that constants are really good at absorbing constants. So if I have 10 times a constant, what do I have? A constant. It's just like, okay, the 10 is absorbed. It's like a constant is like a sponge. And if I have, say, e to a constant, what do I have? It's just a constant, you know. It's just like, so the constant can absorb other constants. And so, all right, now we could solve for x of t right away, or we can say, hey, let's pause and use initial conditions associated with x prime. All right, so 90 is x prime of 1. Okay, that's 10. 1 plus 3 is 4 to the 3/2 power, and then plus c. Now you're probably thinking, oh, well, that's not so bad. 4 cubed is 64, and the square root of 64 is, of course, 8. Now, that's the hard way to do it. We'd really say, oh, 4 to the 3/2 is like 4 to the 1/2. which is 2, and then 2 cubed is 8. So it's 80 plus c. So what does that tell us about c? C is 10. So now we update. Aha! X prime of t is 10, t plus 3 to the 3 halves, and then plus another 10. Okay, we go into round 2. Round 2 being solving the next antiderivative. X of t. What's the integral of 10 times t plus 3 to the 3 halves? Well, 10. T plus 3 to what power now? 5 halves. You can always I'm like, what did they say up there? Oh, yeah, it's 5 halves. Okay. What do we need to multiply by? 2 fifths. And then, okay, I need to integrate 10, which is 10t. And then we need to add a constant. Now, we've already used c, so it's proper etiquette to introduce a new symbol, just so that we don't confuse ourselves and say, oh, wait, plus c, but c is 10. Oh, no. It's a different constant. Well, to finish it up, we need to find of course, what is that constant. So we do, of course, the logical thing. We plug in. We see that 140, big number, is, 10 times 2 fifths is the same as 4. So 140, that's x of 1, which is 4. Then we have 4 to the 5 halves, plus 10 times 1, plus d. Now 4 to the 5th, of course, 1024. And the square root of 1024 is 32. Yeah, right. I know, it just flows. Of course, the other way to do it is the square root of 4 is 2. And then you're like 2 to the 5th. Okay, 2, 4, 8, 16, 32. So this is 32. 32 times 4. Where's our electrical and computer engineers? You're like, powers of 2, that's my jam. Okay. 128 plus 10. 138. So I have 138 plus something. Better give me 140. So what number does that? 2. Ah, that's where the 2 came from. So our final answer is indeed 4 times t plus 3 to the 5 halves plus 10 times t plus 2. All right. Well, let's do a word problem. I have 2 of them. One of them is on the homework, so we won't do that one because that one you can enjoy. So we'll do this one. All right. A spacecraft is heading to the surface of a small moon. So small we can ignore its gravity. Now I know what you're thinking. That's no moon. But all right, that's something else. So the spacecraft is traveling at 1,000 miles, I'm guessing, per hour. 1,000 meters per hour doesn't seem very impressive for a spacecraft. It has rockets which can slow it down at a constant rate of 20,000 miles per hour squared. At what height above the small moon should the rocket start to fire to ensure a soft touchdown? Now you're like, okay, well, when we look for math stuff, like we got these numbers here, so that's kind of math stuff, but that's just about it. There's no like equation right away. And then there's this phrase here, a soft touchdown. What would that mean? What does it mean, 0? People are saying 0, a 0. I'm like, but what does that mean? So you can imagine there's a couple scenarios. So imagine here's the surface of our moon. You can tell it's the surface of the moon because it says it right there, moon. I'm pretty good at this. All right. So there's a couple scenarios. Well, one could be that you don't slow down fast enough, and so you would actually, would in theory be slowing down, but the moon stops you, and that's bad. So that's a hard touchdown. We want to avoid that. And then another thing, of course, you could fire too early, and then you could end up going back into space. And that's no touchdown. And that's also bad. So it's like Goldilocks and the Three Bear. that one's too hard. That one's too soft. But we want the one that's just right. So we want it so that when we hit the surface, we're not moving. We've stopped, but we're at the level. So soft touchdown, the interpretation is at height 0, the velocity is 0. Okay, great. So that's that part. Well, let's see if we can figure this out. Now, a couple of things. This number right here, 20,000 miles per hour squared. What kind of thing is that? What's that related to? Acceleration. Oh, you guys are good. So, and notice it's a constant. So we're told acceleration is 20,000. We won't worry about units. That's a physicist's problem. But is it 20,000? Negative, yeah. Because we're slowing down. So it should be negative. All right. So that's good. So now, well, if we have acceleration, we can get velocity, right? Because acceleration and velocity are related. So what does velocity look like? So, antiderivative, so?
Negative 20,000 t.
Negative 20,000 t. Is that it? Plus c. Now, do we have any information that can help us solve for c? Someone said initial velocity. What is our initial velocity? 1,000. Okay, so we'll have at time t equals 0, our velocity should be 1,000. Great. So we've solved, and I think the one we could probably do in our head, plug in 0. That goes away, so yeah, c should be 1,000. All right, well, wonderful. Now what? Integrate again and get position, right? Because we're really asking about a position. You know, how far should we be starting up? Okay, position for some reason starts with the letter S in physics. At least in calculus textbooks, that's what they always use. Okay, so what is our position function? Okay, so we take the antiderivative, negative 10,000 t squared, 1,000 t plus another constant. We'll use d here. All right. Now, good news. We want to know how high we are at time 0, because that's when we should start firing our rockets. So we plug in 0, and what do we get as our answer? Well, 0, 0, d. So this is our answer. Now, there's one small problem that we have with this particular answer, in that we don't know what the constant is. Yes, our answer is a number. We want to be something more specific. How can we figure that out?
The velocity at height equals 0 should be 0.
Velocity at height 0 should be 0. Huh. So how does that help us? Oh, so people are saying, hey, you should probably use that with velocity. That makes sense. I mean, it's a velocity type thing. We should use it for velocity. Okay, so we have that 0 is negative 20,000 t plus 1,000. All right. Well, okay. Move things around. 20,000 t equals 1,000. Divide. T equals, all right, cancel some zeros. So it doesn't look so intimidating. 1/20. Now, it sounds really quick, but you should remember our units of time are hours. So that's like a couple minutes. So it's like, yeah, a couple minutes, that's okay. I can believe a couple minutes. All right, so that's how long it takes us to go from our initial speed of 1,000 to a speed of 0. And we want to be at our speed of 0 when we're at height 0. So, idea. We plug that in for t, and then we set that equal to 0. Yes? Yeah, that should work. So, 0 minus 10,000 times 1 over 20 squared plus 1,000 times 1 over 20 plus whatever d turns out to be. Okay, so 20 squared is what? 400. So I'm just going to write this as over 400. And then I'll just write this as over 20. Okay, so we can cancel some zeros. Zeros canceling at the end is something pretty nice. 100 divided by 4, 25. So I have negative 25. 100 divided by 2, 50. And then plus d. And so r, that's d plus 25. So d should equal negative 25. Now you're probably saying, wait, negative? Well, we didn't really do a good job with our units here, because we didn't talk about what was the sign of velocity. So we're actually okay. So our answer is 25 miles. That's how far up. Okay, good. Well, there's a minute left. We could talk about the other problem for just a minute, or not. So this is an action-packed problem. It takes more than a minute to read it, but the gist is you've got a helicopter, and I know what you're thinking, get to the chopper, get to the chopper. Okay, so you have this chopper, and it's up 800 feet. And you should always try to draw problems. And then there's this bomb. So at time t equals 0, the bomb starts falling. All right, so then, for some mysterious reason, they wait 2 seconds. And the bomb has kept falling. So now it's falling even faster, because when it drops, it starts at velocity 0. And then there's a rocket that gets fired up. That's going to head up. And then, later on, it turns out, at some unknown time, oh, my time is up. Okay. They still want to hear more. When you get to this point right here, 400 feet, the bomb and the rocket collide, and you make a beautiful explosion. And then the question, of course, is how do you fire the rocket so that this actually happens? Now, so supposing that you were wanting to figure this out, it seems like there's a lot going on. It's a very action-packed problem. So where's the easiest place to start? What do you say, aha, I can completely predict how this will behave? Start with the bomb. Because you know where it's being dropped from, you know it has no initial velocity, and because it's a physics problem, you know gravity is 32 feet per minute, or feet per second. I don't know, that's a physics number, 32, all right. You know how the bomb is dropping. Now, why is that useful? Well, you know how long it takes to drop 400 feet. So you can figure out at what time does this have to happen. Because you can say, I know how the bomb is dropping, so I can say this is how long it took to get to 400 feet. So you can actually find this time. Yes? And now that you know this time, you say, I come back here, and now what you have to figure out is what velocity does this have to shoot up? Well, you say, look, I have this many seconds. I now know this number. I now know its initial height. And then I just have to say, okay, what's the solve for the initial velocity? So that's the idea. So if you're working on that problem. All right. Have a good day.